Hello dear friend, myself Prof. Sabbur HK. Today we learn new topic pressure of an ideal gas. In this video we can discuss the relation between pressure of the gas and speed of its molecule. See this figure. This figure is a cubical box of side capital L. It contains n molecule of an ideal gas. Let there be n molecule of an ideal gas enclosed in a cubical box of volume is this volume this become V is equal to L cube with side of the boxes parallel to the coordinate axis as shown in this figure. The wall of the box are kept at constant temperature capital T. Here a constant temperature capital T. The gas molecule are in a continuous random motion colliding with each other and hitting the wall of the boxes and bouncing back. As per one of the assumption, we neglect intermolecular collision and consider only elastic collision with the wall. A typical molecule moving with the velocity v bar. This is the velocity of molecule v bar about to collide elastically with the saddle wall of the cube parallel to the yz axis. This is the yz axis. YZ planes. During elastic collision, the components v suffix x of the velocity will be gets reverse, keeping vy and vz component unaltered. Hence, the change in momentum of the particle is only in the x component of the momentum. Therefore, delta px is given by delta px be the change in momentum of the particle is only in the x component of the momentum. Hence, this given by delta px is equal to final momentum minus initial momentum. This is a change in momentum of the particle. Here final momentum is minus m vx and initial momentum here become m vx. This is a change means here given subtraction, this change become minus mvx minus mvx. This become minus minus become plus here. Hence, change in momentum of the particle is only in the x component of the momentum is given by here delta px is equal to minus twice mvx. Here we can write here delta px is equal to minus twice mvx. Consider equation first here. This is a change in momentum of the particle is only in the x component of the momentum. Then thus the momentum transfer to the wall during the collision is here we consider plus m plus twice mvx. The rebounds. Molecule then goes to the opposite wall and collide with it. After collision, after collision with the shaded wall, the molecule travel to the opposite wall and travel back toward the shaded wall again. This means that the molecule travel a distance of twice L in between two collision. As capital L be the length of the cubical box, here a capital L be the length of cubical box, we can see in this figure. Here a capital L be the length of cubical box. The time for the molecule to travel back and forth to the shaded wall is given by shear the time for the molecule to travel back and forth to the shaded wall is, this become, this time is time delta t. Delta t is equal to twice L upon px, because our time means what, distance upon speed. Then we can write delta t is equal to twice L upon v suffix x. Then we calculate here average force exerted on the shaded wall by the molecule. First is given by average force means what, average rate of change of momentum. Here average force we can write average rate of change of momentum. Then average force we can write here this average force f suffix average, this become twice m into v suffix x upon, this become twice L upon v suffix x. Then average force we can write here 2m v suffix x into v suffix x, or rearranging this equation we can write here this 2 gets cancel, m v suffix x into v suffix x, this become v suffix x into v suffix x become here square. Average force here, average force is equal to m v suffix x square upon L. Average force, this become m v suffix x square upon L. Therefore according to Newton's second law, the rate of change of momentum is equal to change in momentum upon time. Then we can write this here v suffix x be the x component of velocity of molecule. First, considering other molecule, second, third, fourth, with respect to x component of value velocity, v suffix x2, v suffix x3, uh, up to v suffix x4 up to dot dot, the total average force on the wall is given by, this become average force, average force on the wall is f average is equal to m upon L. Then component of velocities, this become uh, v suffix x1 square plus v suffix x2 square plus v suffix x3 plus up to dot dot. Consider equation number third here. Then we can calculate here the average pressure. Pressure means what? Apply force upon area. Here average force, we can write here pressure is equal to average force upon area of sealed rod. Then this pressure we can write here P is equal to average force M upon L into V suffix x1 square plus V suffix x2 square plus V suffix x3 square plus up to dot dot into area of the sealed rod. This become 1 upon L square. This become here L square, here L square into L, this become L cube. Then this equation we can write here P is equal to the average pressure P is equal to M upon L cube into V x1 square plus V x2 square plus V suffix x3 square. Consider equation number 4 here. The average of the square of x component of the velocity is given by the average of the square of x component of the velocity is given by this become take average, this become v suffix the average of square of x component of velocity, this become v x1 square plus v x2 square plus v x3 square plus v xn square upon n. Rearranging above equation we can write here this become v x1 square plus v x2 square plus v x3 square plus up to plus v xn square is equal to n into v bar x square. Consider equation number 5th here. Put equation 5 in equation 4, we gets here we can write put equation 5 is equation this equation 5 in equation 4th. This is the equation number 4. P is equal to m upon L cube into v1 square plus vx2 square plus vx3 square plus up to dot dot. Then equation 4th become here we can write P is equal to m into n v suffix x square upon L cube. Consider equation number 6 here. But we know that v is equal to L cube, volume is equal to length into length into length. Then equation 6 become P is equal to m into n v suffix x bar square upon v. Consider equation number 7 here. V suffix x bar be the is the average overall the possible value of v suffix x. Now v square bar, this become vx square bar plus vy square bar plus vz square bar. By using this symmetry we can write here this become v square bar plus vx square bar plus vy square bar plus vz square bar. By using symmetry vx square bar is equal to vy square bar is equal to vz square bar. Then we can write here 1 by 3 v square bar. Consider equation number 8 here. Put equation 8 in equation 7, we gets we can write value of this P is equal to 1 upon 1 by 3 into m into n into v square bar upon p. Since the molecule have no perform direction to move, therefore average pressure, this become p is equal to, here p is equal to, p is equal to 1 by 3 n upon v into m into v square bar. Consider equation number 9 here. This is a relation between pressure of gas and speed of a molecule. This equation number 9. This is the relation between pressure of gas and speed of its molecule. Some question asked on this topic. Prove the relation between pressure of the gas and speed of molecule. Prove the relation between pressure of the gas and speed of the molecule. Next topic is an expression for root mean square speed of a molecule of a gas in term of absolute temperature. Next point we can discuss here, an expression for root mean square speed of a molecule of a gas in term of a its absolute temperature. Here average value of pressure of the gas is given by here, p is equal to 1 by 3 n into n upon p into m v square bar. Thus the mean square velocity of molecule will be mean square velocity, this become v square bar is equal to thrice pv upon n into small m. Consider equation first here. Using ideal gas equation, we know that ideal gas equation pv is equal to nRT. Then put equation second in equation first, we gets v square bar is equal to thrice n into RT upon capital N into small m. But we know that here n is equal to small n is equal to capital N upon n suffix a. Then above equation we can write here uh, small n is equal to capital N upon n suffix a. The above equation become v square bar is equal to thrice RT upon capital N into m into n. We can write here v square bar is equal to thrice RT upon capital N into m into capital N into n suffix a, capital N upon n suffix a, because n is equal to this. Then rearranging this equation, n and gets cancelled here, remaining what, v square bar is equal to thrice RT upon n suffix a into m. Consider equation number third. Also we know that m into n suffix a is equal to m suffix 0, small m into n suffix a is equal to m suffix 0. This m suffix 0 means molar mass of the gas. Then we can write here v square bar is equal to thrice RT upon m0. Then we can write here root mean square velocity that is here we can write VRMS is equal to square root of thrice RT upon M0. Here taking square root, then mean square velocity, this become root mean square velocity is equal to square root of thrice RT upon M0. M0 be the molar mass of the gas. Then we can write PRMS root mean square velocity, this becomes square root of thrice RT upon M0. Consider equation 5. This is an expression for root mean square speed of molecule of a gas in term of a absolute temperature. In term of absolute temperature, question asked on this topic is derive an expression for root mean square speed of a molecule of a gas in term of its absolute temperature. Okay, uh, I repeat this question. Derive an expression for root mean square speed of a molecule of a gas in term of its absolute temperature. Then we can derive this equation, become V suffix RMS is equal to square root of thrice RT upon M0. Then next note, some question asked here: what will happen to the mean square speed of the molecule of a gas if the temperature of the gas increase? Okay, what will happen to the mean square speed of molecule of a gas if the temperature of the gas increase? What happen here? The mean square speed of the molecule of a gas, we can write here mean square speed, this become p square bar is equal to thrice RT upon M0. Here thrice, here 3 is a constant, R also constant, M0 also constant, M0 also constant. uh, then we can write here um, V2 square bar directly proportional to T, because all term is a constant. 3 constant, R constant and M0. Hence the mean square speed of molecule of the gas increase the same proportion with the increase in a temperature. Here temperature increases, corresponding mean square speed of molecule of the gas also increases. And another one, second notes, for nitrogen gas at 300 Kelvin, the root mean square speed is 517 meter per second, while for oxygen gas it is 483 meter per second. Same temperature for hydrogen gas at 300 Kelvin, the root mean square speed is 517 meter per second, while for oxygen gas it is a 483 meter per second. Another notes, when the gas is heated, the molecule of the gas acquire the energy and their RMS velocity, that is a root mean square velocity, increase according to kinetic theory of a gases. Root mean square velocity, this become uh, VRMS directly proportional to square root of T. Here increase in a, here increase in a VRMS led to increase in VRMS led to increase in the temperature of the gas. Hence, when a gas is heated, its temperature increases. And question asked on this topic: when a gas is heated, its temperature increase. Explain this phenomena based on kinetic theory. Next question is: and fourth one, the relation between speed of sound in a gas and the RMS speed of the gas molecule. First, this become speed of the sound in gas. We can write here, or write here v suffix x, speed of sound. This become square root of gamma into RT upon m0. Here gamma is equal to Cp upon Cv is called as a adiabatic ratio. Maximum value of gamma is 5/3 for monoatomic gases. Okay, and next one, root mean square speed of the molecule. Root mean square speed of a gas molecule is Vrms is equal to square root of thrice RT upon m0. Next, the speed of wave cannot move faster than the average speed of the molecule since gamma less than 3. However, however, the two speed are of the same order of magnitude. Then we can share the molecule serve as a medium to transport sound energy. The speed of sound in H2 gas is comparable to the RMS speed of H2 molecule and N2 gas to the RMS speed of the N2 molecules. In this way, we complete this point. Some question asked on this topic: comment about the relation between speed of sound in a gas and the RMS speed of the gas molecule. Today in this video we can discuss firstly an ideal gas, pressure of ideal gas. Then we can discuss the relation between pressure of the gas and speed of its molecule. And another one, we can discuss here an expression for root mean square speed of a molecule of gas in term of an absolute temperature. And some notes we can discuss here: the mean square speed of molecule of the gas increase in same proportion with the increase in temperature. Here temperature increases, corresponding mean square speed of molecule also increases. In this way we complete this point. Today we stop here. Thank you.